Very good evening, students.
Good evening,
Good
sir.
Good evening, all. Let us start the discussion without wasting any time. So, if you remember,
Good evening, sir.
last class we have been discussing about the preparation of respective colloids. In that, the concept which we have discussed is peptidization. The process of converting a freshly prepared precipitate into colloidal solution by shaking it with dispersion medium in the presence of small amount of electrolyte, that is said to be peptidization. So, the electrolyte whatever you have added, that is nothing but your peptidizing agent. So, this was the reaction. AgNO3 I am trying to add to Ki. You are getting respect to AgI, which was a PPT, and that AgI is in the precipitate form. That means it is like suspended. We are trying to add some electrolyte. No, that electrolyte will be having positively charged ions as well as negatively charged ions. These ions will preferentially adsorb on the surface of the respective precipitate and make the precipitate to split down into the particles of colloidal range. So this is how the mechanism or the reaction is going to happen. AgNO3Ki formed respect to AgI. This is your respect to AgI, and we have the respect to electrolyte. Those electrolytes will make the splitting of respect to precipitate into a smaller sized particles which are in the colloidal range, and that is how you can have the respective that is how you can be having the respective peptidization or colloidal system formation. So how now the dispersed phase and dispersion medium, they are going to be decided, and what type of charge is going to be developed, that we'll study now. AgNO3, if you are trying to add to Ki, where you are forming AgI and KNO3. Now let us take, let Ki be the dispersion medium. Let Ki be dispersion medium. So in Ki we have what ions? That is, we have excess of K plus and I minus ions. So on the AgI, which ion can adsorb? If Ki is the dispersion medium, we have K plus ions as well as I minus ions. In the AgI, which ion can adsorb? Either K plus ions or I minus ions? AgI is a PPT form, right? We are adding AgI and Ki, AgNO3 and Ki. AgNO3 Ki, whenever you try to add, you form AgI, which was a precipitate. In that PPT AgI, you are adding AgNO3 and Ki in such a way such that Ki is the dispersion medium. That is, it is a solvent now. We have more Ki. Dispersion medium means we have more of that particular solvent, more Ki is there. Let Ki be the dispersion medium. Then we have excess K plus and I minus ions. So on the AgI, among K plus and I minus, only the common ion will adsorb. So AgI will adsorb only I minus, and we have K plus ions surrounding the I minus. So AgI is the respective colloidal particle. On that AgI, we have negatively charged I minus. This is a fixed layer. The negatively charged I minus is the fixed layer. Around the negatively charged I minus, we have a diffused layer as well. We have a diffused layer of a positively charged K plus ions. Understand this point carefully, all of you. Around this diffused layer, around this fixed layer, we have a diffused layer. The second layer is a diffused layer. The first layer is actually the fixed layer, and between these two layers, the electropotential developed. It is also nothing but zeta potential. Yes or no? There is some potential developed because two opposite charges are separated by some distance. So there is some potential developed. That potential is said to be zeta potential or electrokinetic potential, and the common ion is going to be adsorbed preferentially. The I minus is going to be adsorbed on AgI. So it will be what type of sol? Negatively charged sol. Negatively charged sol. Now let us take the scenario later. AgNO3. Let AgNO3 be dispersion medium. Earlier we have taken Ka to be dispersion medium. Now AgNO3 be dispersion medium. So AgI, we have excess of Ag plus and NO3 minus. So NO3 minus and Ag plus. Out of this, which is the common ion in the respect to PPT?
AG.
Plus. So Ag plus will be respectively adsorbed, And what happened to KNO3 minus? KNO3 minus will be acting as a diffuse layer around Ag plus. We have the colloid where we have positively charged Ag plus will be absorbed, and we have the diffuse layer where we have the negatively charged NO3 minus ions will be surrounding. Yes or no? So it leads to the formation of positively charged sol. Positively charged sol. Right? So this is how the charge formation can be explained, understood? Few examples of salts obtained by peptidization. AgI plus AgNO3. AgI is a PPG and AgNO3 is a dispersion medium. AgNO3 dispersion medium, so Ag plus is a common ion. So that get absorbed. To get AgI on the PPT, you have Ag plus absorbed, which is a fixed layer, and this is a diffuse layer. This is a fixed layer. Fixed layer, that is absorbed ions, and this was a diffuse layer. So it is not fixed, it is just having electrostatic force of attraction with Ag plus. AgI plus Ki. So among K and I minus is the common ion. So AgI and I minus is getting absorbed, surrounded by K plus ions. FeOH taken thrice plus FeCl3. On FeOH taken thrice FeCl3, we have Fe plus 3 as a common ion, right? Fe plus 3 will be respectively absorbed, and chloride ions will be the diffuse layer. FeOH taken thrice plus NaOH. OH minus is a common ion. So FeOH taken thrice, OH minus and Na plus will be the respective diffuse layer ions. Cadmium sulfide plus H2S, these are all the precipitates. On the precipitates, the ion, the common ion is actually getting absorbed from the dispersion medium. From the dispersion medium, whatever the common ion we have, that is actually getting absorbed. So cadmium sulfide will be getting absorbed by sulfide ions, and H plus ions will be present in the diffuse layer. Is that clear or not?
Yes, sir.
Common ion of PPT and dispersion medium will get absorbed on the colloidal particle. Right. The process of peptidization thus involves the adsorption of suitable ions, particularly a common ion. The process of peptidization involves the adsorption of suitable ions. What are the suitable ions? Particularly a common ion is going to be getting absorbed. The same FeCl3 plus H2O hot, you generate FeOH taken thrice. FeOH taken thrice plus FeCl3 will be giving what? The Fe plus 3 is a common ion that get absorbed. FeOH taken thrice is a PPG. On that Fe plus 3 got absorbed, it is a fixed layer. 3 chloride ions, they are present as diffuse layer. Same FeOH taken thrice is a PPG on which OH minus absorbed. So we have FeOH taken thrice OH minus and Na plus is the diffuse layer. So these are the reactions where you are forming respective type of colloidal particles using peptidization. Earlier we have seen the reaction of Briggs-Stark method. This is nothing but your peptidization. And then we also have chemical methods. What are the different chemical methods we can have? Double decomposition we can have, oxidation we can have, reduction we can do, hydrolysis we can do. Like this is nothing but hydrolysis or not. FeCl3 plus H2O forming FeOH taken thrice. And if you maintain FeCl3 as the dispersion medium, we have respect to FeOH taken thrice absorbed by Fe plus 3. This is nothing but a hydrolysis reaction. So next type of method of preparation of colloidal particles are chemical methods. And all these methods are used for the preparation of lyophilic sol or lyophobic sols.
Lyophobic.
Because lyophilic, they can be simply prepared by adding the dispersion medium and dispersed phase. Why? Because there is an affinity between dispersion medium and dispersed phase. Chemical methods, double decomposition, AS2O3 plus 3H2S will be forming respect to AS2S3 sol, arsenic sulfide sol, and H2O is obtained. So arsenic from the plus 3 state went to again plus 3 state, sulfide from the minus 2 went to minus 2. So both has been decomposed. AS2O3 and H2S will be forming AS2S3 and respective water is formed. Oxidation, SO2 plus 2H2S will form 3 sulfur plus 2 H2O. The sulfur from the minus 2 state went to 0 state. It is nothing but your oxidation. Sulfur sol is obtained. AS2S3 is a sol which is negatively charged sol. We'll categorize based on charge. We'll categorize all types of salts. Reduction also we can do to produce respective gold salt. Double decomposition, oxidation, reduction, AuCl3 plus 3HCHO plus 3H2O undergoing reduction to form 2Au, gold salt. Along with that, Hc double bond OH and 6HCl are obtained, and this will be lying in the range of 1 to 1000 nanometers. Then only we can call this as a colloidal particle or salt. And also after reduction, we can also think of hydrolysis. In the hydrolysis, same ferric hydroxide salt can be prepared. FeCl3 plus 3H2O forms FeOH taken thrice, which is a ferric hydroxide salt, which is again lying in the 1 to 1000 nanometer range. These are the chemical methods. The Bredig-Sark method, the peptidization, the chemical methods, these are the methods of preparations especially applied for lyophobic salts because they do not have any affinity between the dispersion medium and dispersed phase. Dispersion medium and dispersed phase do not have affinity. That is why these are actually prepared by special methods. Is that clear, students?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, right. Very good. So then we can have the purification of colloidal particles. Like purification, in that purification techniques, we have dialysis, electrodialysis, ultrafiltration. So what do you mean by this purification? Like I have told you, a small quantity of electrolyte is essential for stabilizing the colloid. But if the quantity of electrolyte is high, then the coagulation can occur. Understand this point carefully. A small quantity of electrolyte, is essential for stabilizing the colloid. But if the quantity of electrolyte is excess, then it will lead to the formation of coagulates. It will lead to the aggregate formation. Whenever we have a small quantity of electrolyte, these ions, they are going to be absorbed on the respective particles, so that the colloidal particles are going to develop a charge. Because the colloidal particles develop a charge, they will not form coagulates. They will not form any coagulates. But in case if we have more electrolytes, then all these electrolytes will going to be absorbed on the respective particles. All these electrolytes, they will be getting like some electrolytes will be absorbed, right? So colloidal particles will have charge. Some, let us say, all the colloidal particles are positively charged. Then the extra negative ions, whatever they are present due to electrolyte, they will neutralize the charge, making the coagulation happening. So that is why there is a high need to purify the colloidal solution to make it stable. So in that purification techniques, we have three processes like dialysis, electrodialysis, and ultrafiltration. In dialysis, what you are going to do? Let us look one by one. Dialysis. In dialysis, we pass the water. Because of the flow of water, what happens? We have taken a colloidal system in a particular beaker, and we have a semi-permeable membrane. Through the semi-permeable membrane, only the crystalloid particles can move away, not the colloidal particles. So along with the flow of water, what happens? All the crystalloids are moving away, and the colloidal particles will lie in that only. So that is how the separation can be done. Dialysis and electrodialysis, what was the difference? In the electrodialysis, we try to separate the colloidal particles from crystalloid particles by applying electric field. Dialysis is just the separation happening with the flow of water. Electrodialysis means by using of electric field also. The process of separating the particles of colloid from those of crystalloid by means of diffusion through suitable membrane, that is called as dialysis. Like its principle is simple. It is based upon the fact that colloidal particles cannot pass through parchment or cellophane membrane. while the ions of electrolyte can pass through it. The electrolyte ions, they can pass through it, but the colloidal particles are not passing through it. That is how we can separate the particles of colloid from crystalloid. Is that clear or not?
Yes, sir.
Simple.
Yes.
The animation also very clear. The apparatus used for this process is dialyzer. A bag of suitable membrane containing the colloidal solution is suspended. We have to take a bag of suitable membrane containing the colloidal solution is suspended in a vessel through which fresh water is continuously flowing. With the flow of water only, all the crystalloid particles, they are moving away, whereas colloidal solution is left behind. The molecules and ions diffuse through membrane into the outer water, and a pure colloidal solution is going to be left behind. If you try to do the dialysis continuously, prolonged dialysis, it will cause what? If you try to do the prolonged dialysis, can I say all the crystalloid particles will be removed? If all the crystalloid particles are removed, then the colloidal particles will not be developing any charge. Why? Because the charge on the colloidal particle is because of absorption of the ion. If all the electrolyte particles are removed, there is no absorption happening, there is no charge. So prolonged dialysis will also cause what? Coagulation. Yes, precipitate formation or coagulation. Electrodialysis is same technique, but this technique is actually used to separate the crystalloid from colloid with the application of electrical field or electric field. The process of dialysis can be made faster by applying an electric field if the dissolved substance in the impure colloidal system is only an electrolyte. Understand this point carefully. Whatever the impurity we have, right, if that impurity is only an electrolyte, then only we can apply the electric and magnetic field, so that the electrolyte which has ions, positive ions and negative ions, the positive ions will move towards negatively charged plate, the negative ions will move towards positively charged plate. But in case if the impurities are non-electrolytes, which are neutral in nature, then they will not be separated. Okay. This process is only used when the impure colloidal solution is only an electrolyte. Like this is a technique. So when you are doing the flow of water also, and whenever you try to apply the electric field, some cations, positively charged ions will move towards cathode, negatively charged ions will move towards anode, and the crystalloid particles wants to move, but they are not allowed to move through semi-permeable membrane because the pore size is smaller. Okay, because the semi-permeable membrane cannot allow the colloidal particle to flow through it. So that is how whenever you do the electrodialysis, it is just fastly separating the respective colloidal solution. Ultrafiltration. Ultrafiltration means normal filter paper. Like if you take the normal filter paper, the pore size is going to be larger. Because of larger pore size, the colloidal particles cannot be separated. What you are going to do is you have to place the normal filter paper into a solution of like colloidal solution, and you have to make it hard. So whatever the pore size you are getting here, that is going to be getting reduced, and the filter paper whatever you obtain, that is said to be ultra filter paper. This ultra filter paper whose pore size has been reduced, that is used to separate the crystalloid particle from the colloid particle. Colloid particle can move through filter paper, it cannot move through ultra filter paper. Okay, you may ask a question, sir, how this pore size has been reduced? By dipping the filter paper in the colloidal solution. So what is colloidal? We'll discuss that. Salt particles directly pass through ordinary filter paper. Salt particles means colloidal particles directly pass through ordinary filter paper because their pores are larger than the size of salt particles or colloidal particles. If the pores of ordinary filter paper are made smaller, how? By soaking the filter paper in a solution of colloidon. What is colloidon? Colloidon is a 4% solution of nitrocellulose in a mixture of alcohol and ether. 4% solution of nitrocellulose in a mixture of alcohol and ether, that is nothing but colloidal. Whenever you try to soak the filter paper in a solution of colloidal and that is subsequently hardened by soaking in formaldehyde, then the new filter paper obtained is said to be ultra filter paper. The treated filter paper may retain colloidal particles and allow the true solution particles to escape. Such a filter paper whose pore size has been reduced, that is said to be ultra filter paper, and this purification technique is ultrafiltration. This purification technique is ultrafiltration. Is that clear, students?
Yes, sir.
Yes, sir.
Yes, right. Very good. So these are the three purification techniques of colloidal solutions. Then we can have different properties of colloidal solutions. Properties, if you try to think of, first is very simple. Colloidal solutions as well as suspensions, they are heterogeneous in nature because we have two different phases. Dispersion medium and dispersed phase, there are difference in the phases. And we have filtrability. In the filtrability, what you can say, colloidal particles pass through ordinary filter paper but do not pass through parchment and other fine membranes or ultra filter paper, like ultra filter paper. So there was a difference, like the filterability properties have been differed for colloidal particles as they can pass through the filter paper but cannot pass through parchment paper or the ultra filter paper. It is a colloidal particles or colloidal solution is a heterogeneous mixture. Visibility, can we see the colloidal particles? Colloidal particles cannot be seen with the naked eyes. Colloidal particles, however, scatter light and become visible as bright spots in a dark background when seen through a ultra microscope. Like in the movie theaters also we have the same scenario. Like from the projector, whatever light is falling, that will be on the screen, and you have many dust particles which are in the colloidal size. On those dust particles, this light is falling, the electromagnetic radiation. Those colloidal particles will scatter the light in all the directions. That is why you can observe whatever dust particles we can see in the movie theater, they will be appearing as bright spots or not. Yes or no? The colloidal particles in the dark background, they appear as bright spots because they scatter light. Colloidal particles cannot be directly visible with the naked eyes, but they can scatter light and become visible as bright spots in the dark background, like stars. They are visible like stars. In 1903, Zsigmondy devised a microscope which is based on the principle of scattering of light by Sol particles. So we can look at that principle. Like we have the gold Sol, we have NaCl solution, we have tobacco smoke, and we are passing the source like electromagnetic radiation. Through the gold Sol, light beam is visible. Through the NaCl solution, light beam is not visible. Through again tobacco smoke or aerosol, light beam is visible. What do you understand from this? Whenever the source or electromagnetic radiation has been passed to the respective solutions, one is colloidal solution, the other is true solution, again is a colloidal solution. The colloidal particles, they are scattering light but not the particles in true solution. Why?
Because their size is much larger as compared to wave.
The colloidal particle size and the wavelength of the electromagnetic radiation, that has to be, that difference should not be very high. If the wavelength of the light is much higher when compared to the size of the true solution particle, then obviously the electromagnetic radiation cannot interact with that small sized particle. So you cannot, that small sized particle cannot scatter the light. Yes or no? So we can say small size particle, large size particle. Okay, crystalloid. This you can see as colloid. Although this is not the correct way, exact correct way to represent, but you can understand it easily in this fashion. Because the wavelength, the electromagnetic radiation which has a wavelength, that has to interact with the colloidal particle, then only the scattering will happen. Surface tension viscosity. If you try to understand viscosity of colloidal solution, like lyophilic sol you take, lyophobic and lyophilic, two salts you take. Lyophilic sol will have More viscosity or less viscosity?
More
Lyophilic.
More
viscosity.
Whereas surface tension,
Less surface
Less
tension.
less surface tension. But if you throw with the lyophobic sol will have
same as that of solvent.
same as that of solvent. These are the same properties which you have discussed. Again, repetition of those properties. For lyophobic salts, surface tension and viscosity are not very different from those of the dispersion medium or solvent. Why? As there is very slight interaction between suspended particles and the medium, because dispersed phase particles and dispersion medium do not have good interaction. The difference in the surface tension and viscosity for lyophobic sol and the dispersion medium, that is not high. On the other hand, lyophilic salts show a high degree of solvation of the particles, and therefore the properties of the medium are modified. That means the viscosity is much higher for the sol. Why? Because the particles are not now easily flowing, because their motion has been reduced because of hydration. Furthermore, the surface tension of the sol is lower than that of pure medium. Why? Because whatever the particles we have on the surface, they are now coming down and developing attraction with the sol particles. Surface tension is lowered, viscosity is higher. That is how you can understand the lyophilic sol. For lyophobic sol, what you can say? Surface tension and viscosity, they are same as that of dispersion medium. Very good. Color. Color, can you observe? Color of the colloidal solution, if you try to think of, it depends upon many factors like wavelength of scattered light and the manner in which the observer is receiving the light. This is very, very important. Like if there is some matter here, this is some matter, and we have source. From the source, we are getting the light. The light is falling on the matter. And now I am observing, I am the observer who was standing in the direction of transmitted light. In the direction of the transmitted light only, like in the direction of source light only, I am trying to observe the color. Then I can see different color for the same particle. And this, after the electromagnetic radiation interacts with the matter, you will have some scattered light. And now I am observing the same scattered light. Then from the scattered light, I'll have different color. So this color depends upon what? First is the size of particle, because if I try to change the size of particle, the interaction with electromagnetic radiation, that changes. Nature of particle, because in that particle, the electronic transitions, they'll again decide the color. So size of particle, if the size of particle is differed, whether it is going to absorb the electromagnetic radiation or not, that differs. Nature of particle based on the transitions interacting in that particular substance, and the manner in which the observer receives the light. So when I observe the same matter from the along the direction of source light, I'll have a different color. If I try to observe the scattered light, I'll have a different color. Okay, so these are the different, like here we have a source. Here somewhere we have a source. From the source particle we have, this is a colloidal system. From the source, the electromagnetic, here we have source, and this is a colloidal system. From the source we are having light, and I'm standing here only. I'm observing the same particle. I am observing the sol particle in the direction of source light. Then I'll have different color, because what I'll see, the energy required to exert the electron, that can be observed. Like that energy is going to be taken by the species, and the left out radiation also can observe. I can see the same system standing here, same particle, same source, same colloidal particle, but now I am looking at the colloidal particle from here. So the way in which you are observing the same colloidal system, if that is changing, then the color obviously changes. So the color of silver song changes with the diameter of particle. Obviously, if you try to change the diameter, the interaction as interaction of electromagnetic radiation changes. Electromagnetic radiation changes. Finest gold sol is red in color. As size of particle increases, it appears purple, then blue, and then finally golden. Finest gold sol is red in color. Again, if you try to change the size, it appears purple and then blue and then finally golden. Mixture of milk and water appears blue when viewed by reflected light, but red when viewed by transmitted light. So whenever you try to change the position of the observer, again the color is going to change. Is that clear or not?
Yes, sir.
Yes or no?
Yes, sir.
Right. Colligative properties. What are colligative properties? From the solutions, what you have understood?
Which obey Raoult's law.
Colligative properties depend upon what? Depend upon the number of particles or not?
Yes.
Yes, sir.
Colligative properties are those properties which mainly depend upon the respective number of particles. If the number of particles changes, then only we have introduced the Van 't Hoff factor I. Like whenever we have a non-volatile solute as an electrolyte, dissociation of that electrolyte will happen to produce ions. So if the number of ions changes, the number of particles obviously changes, means colligative property changes. Relative lowering in vapor pressure, elevation in boiling point, depression of freezing point, osmotic pressure, all these are depending upon number of particles. But the particle size, if you try to compare for true solution and colloidal solutions are much bigger in size when compared to true solution. Since the colloidal particles are much larger in size, can I say, the number of colloidal particles will be less. When compared to the number of particles in the true solution, the number of particles in the colloidal solution will be less or not?
Yes, sir.
Yes, sir.
Obviously, because they are having large size, the number of particles is less in colloidal solution, so the colligative properties will be less or more?
Less. Less.
Less. So number of particles greater means colligative property will be higher. So these colligative properties, you can neglect it for colloidal solutions as the number of particles is less. Colligative property depend upon relative number of solute particles in solution. In the case of colloidal solutions, colloidal particles are the aggregates of ions or molecules, and when compared to two solutions or normal solutions, the number of particles of solute in solution are very less due to large size, and hence these colloidal solutions exhibits colloidal properties to a lesser extent. In simple words, what you can say, less number of colloidal particles are there, so obviously their colligative properties are less, so you can neglect the colligative properties for colloidal systems. Then we can have optical properties like salts exhibit a Tyndall effect. This is a light source, and here we have a colloidal solution. From the light source, you are having the respective electromagnetic radiation that is falling on the particle, and you can see the Tyndall coal formation. This particle is actually reflecting the light. This particle is actually scattering the light in all the directions, and if you try to observe that particle with the help of a microscope, you can see that clear scattering of light by that particle. This scattering of light by colloidal particle can happen under two conditions. What are two conditions? First thing, wavelength of the electromagnetic radiation and diameter of the colloidal particle, they should not differ much. Second point, can anyone think of second point? Like wavelength, the diameter of the dispersed particle is not much smaller than the wavelength. If it is much smaller than the wavelength, what you can say? Then no interaction will happen with respect to electromagnetic radiation. Second point, the refractive indices of the dispersed phase and dispersion medium, they should differ greatly. They should be differing greatly. Under those two conditions only, you can observe the Tyndall effect. Okay, when light is focused on a sol and observed perpendicular to the beam of light rays, a cone is seen, which is called as Tyndall cone. This was first observed by Faraday and later studied in detail by Tyndall, and that is why it is known as Tyndall effect. Tyndall effect can be observed during the projection of picture in the cinema hall also, due to scattering of light by dust and smoke particles present there. You can see the particles which are present in the theater, they can be seen as bright spots because you are observing those particles perpendicular to the direction of electromagnetic radiation hitting them. Yes or no? I am standing somewhere here, somewhere backside we have a projector, somewhere at the front you have the screen, and we have all the dust particles. I am observing the dust particle from here. I am observing the dust particle from the perpendicular direction. So scattering of light can be clearly visible, and that a colloidal particle can be seen as a bright spot. There are some conditions, as I have told you. Tyndall effect can be satisfied or observed only under the following conditions. Tyndall effect can be observed only when the following conditions have been satisfied. What are the conditions? Diameter of dispersed particle is not much smaller than wavelength of light used, because dispersed particle is much smaller in size when compared to the wavelength of the light. Then no interaction will occur. No interaction will occur with the electromagnetic radiation and the particle. Next one, what's the next factor I have told you?
Refractive indices.
Refractive indices, very good. Refractive indices of the dispersed phase and dispersion medium, they should differ greatly in magnitude. Under these two conditions, you can have Tyndall effect is going to be observed. Under these two conditions, you can have Tyndall effect going to be observed. Right? Next one, visibility. Colloidal particles can we see with the visibility? I think we have already discussed, right? Colloidal particles cannot be seen with naked eye. We can see with the help of ultra microscope. We have seen this, right? Like gold particles, light beam visible, light beam not visible, light beam visible. So with respect to visibility, again you can talk of these perspectives, because colloidal particles can scatter the light, whereas NaCl solution, that is not going to scatter the light because the particle size is much smaller. Kinetic properties. What kind of kinetic properties you can observe for colloidal particles? Kinetic properties, what kind of kinetic properties you can say? When a sol is examined with an ultra microscope, like there was some zigzag motion for the colloidal particles. Colloidal particles do not settle down. Even though I have a colloidal system, like even though I have milk is an emulsion which is a colloidal system. If I keep the milk separately, will it settle down, the dispersed phase particles?
No, sir.
No, that is not going to. Why? Why that is not going to happen? But centrifugal.
Brownian motion.
Yeah, Brownian motion. Very good. The continuous rapid motion of the colloidal particles is present in the dispersion medium, and this continuous motion you can understand because of collisions. Lot of dispersion medium particles are there. The dispersed phase particles continuously collide with the dispersion medium particles, and you will have a lot of zigzag motion. That zigzag motion is nothing but Brownian motion. Because of that, settling of the colloidal particles will not happen due to gravity, but because of centrifuge, settling may happen. Okay. So when a sol is examined with an ultra microscope, it is observed that the particles are in a state of continuous motion in zigzag path. The continuous rapid zigzag motion of colloidal particle in the dispersion medium, that is called as Brownian motion or Brownian movement. This was actually first observed by a British botanist, Robert Brown. This motion is independent of the nature of colloid, but depends on the size of the particle and viscosity of the solution. Yes, Karthik, whatever the particles which are not visible to you with your naked eye, but they are visible whenever we have a particular light falling on them, that is that they are visible with the help of scattered light, they are all colloidal in nature. Okay. If you cannot directly see the particle, like if I directly see in the nature, if I cannot observe a particle, that is not a colloidal particle. Like if I cannot see the particle, but I can see the scattered light of that particle, then that is said to be colloidal particle. Okay. Actually, we are surrounded by colloids. Everywhere we have colloids. The delta formation is a colloid. The blue color of the sky is a colloid. As I have told you, the applications, we are actually surrounded by colloids. The air itself is a colloid. Okay. This motion is independent on the nature of colloid, but depends on size of particles and viscosity of the medium. And this is complete due to colloids, collisions between dispersed particles with the dispersion medium. Smaller the size and lesser the viscosity, faster is the motion. Small size particle, less viscosity, so more fastly the motion will be there. The Brownian motion is due to unbalanced bombardment of the particle by the molecules of dispersion medium. That means they are continuously colliding because no particle is static. Molecular motions are always there. It is a solution. Molecular motions are high. Of course, less when compared to gaseous phase, but still they are high when compared to solid phase. So molecular motions are continuously there. So dispersion medium is like a solvent. Very high number of dispersion medium particles are there. So collision is going to happen. Because of collision, what is going to happen? Because of continuous collision, we have a zigzag path, which is nothing but Brownian motion. The Brownian motion has a steering effect. Due to that, particles do not settle. The settling will not happen. And this is responsibility for the stability of Sol. If the particles all settle down, because of collision, there may be a disturbance of charge. You can observe the students. If a colloidal particle which is charged, if it is hitting this particular dispersion medium particle, the charge is what? The charge is due to fixed layer. That fixed layer can be disturbed or not due to collision.
Yes.
Yes.
So that charge can be lost because of collisions. But there are no balanced collisions. All the collisions are unbalanced. So that is why they will not come down or settle down at the bottom, and they will not form an aggregate. Charge on the colloidal particles, as I have told you, here only the concept of zeta potential comes into picture. Colloidal particles always carry an electric charge. If you take lyophilic also, there is some charge. Less charge will be there. So the charge might be due to two reasons. What is the first reason which you have think up to now?
Preferential absorption.
Preferential adsorption of a respective ion, of common ion. The other reason which you can think of in metal salts are there. No, there the electron capture can be caused. The electron capture in the presence of metal salts is also the reason for the charge. That is why most of the metal salts are negatively charged. So there are two reasons. First thing is colloidal particles always carry an electric charge. First thing is the nature of charge is same and equal on all the dispersed particles in a given colloidal solution. If you have 10 particles, all the 10 particles will have same type of charge and same quantity of charge. Let us say all of them are positively charged, and if Q is the charge on one particle, same plus Q will be the charge on other particle. You cannot have some 5 particles with plus Q, some other 5 particles with minus Q. You cannot have some particles with plus Q, some particles with plus 2Q. That is also not possible. Same charge, same quantity of charge, and also same type of charge. The mutual force of repulsion between the similar charged particles prevent them from aggregation and thus settling under the action of gravity. So this gives stability to the solution. The charge on the Sol particle is due to one or more reasons. What are the reasons? Due to electron capture by sols during electron dispersion of metals. When you do the electron dispersion of metals, electron can be captured on the Sol particle. Thereby the Sol particle can be negatively charged. Okay. That's why metal salts are negatively charged. Due to preferential adsorption of ions from solution and/or due to the formation of electrical double layer, where you can have the potential developed here known as zeta potential. One layer, like one on the Sol particle, one is the fixed layer which got adsorbed, and around the fixed layer we'll have one more extra layer, which is diffuse layer. Between the fixed layer and the diffuse layer, what are the potential we have? That is nothing but zeta potential. electrical double layer formation. You can see this electrical double layer formation clearly. We have the salt particle, one layer, one is a fixed layer, other is a diffuse layer. The diffuse layer will be moving around the fixed layer. Fixed layer is due to adsorption, preferential adsorption of ions on the salt particle. Because of preferential adsorption only, that particular salt particle has a charge. Around that particular charge, we have another type of ions moving. The combination of two layers of opposite charges around the salt particle is called as Helmholtz double layer or electrical double layer. The first layer of ions is firmly held and is called as fixed layer or compact layer. The second layer is mobile, which is termed as diffuse layer. The first layer of ions is firmly held. That is why it is also called as fixed layer or compact layer. The second layer is mobile. Mobile means it is under motion. It is diffuse. It is not fixed. And that is why it is said to be diffuse layer. The diffuse layer is only loosely attached to the particle surface and moves in the opposite direction under the applied field. If salt particles are moving in one direction, the diffuse layer moves towards the other direction. Because salt particles, if they are positively charged, the negatively charged ions will form a diffuse layer. So the diffuse layer is only loosely attached to the particle surface and moves in opposite direction under the applied electric field. The potential difference between the fixed layer and the diffuse layer of opposite charge, that is called as electrokinetic potential or zeta potential. The potential difference between the fixed layer and the diffuse layer of opposite charge, that is called as electrical double layer. Is that clear or not? The same points,
sir.
whatever we have explained, we are seeing in the slides. The addition of more electrolytes to salt suppresses the diffuse double layer and reduces the zeta potential. The addition of more electrolytes to the salt. If you try to add more electrolytes to the salt, what happens? That suppresses the diffuse double layer. Why? Because electrolytes we have cations and anions. The diffuse layer is opposite to that of charged particle. Whenever we have diffuse layer like positive or diffuse layer negative surrounding the positively charged salt particle, I have added an electrolyte AB. AB has A plus and B minus ions. The A plus ions can attract the diffuse layer ions or not. So when you try to add electrolyte, the diffuse layer is developing new attraction with the electrolyte ions, thereby reducing the zeta potential. This decreases the electrostatic repulsion between particles to a large extent and colloid precipitates. If you try to remove all the layer, diffuse layer, what happens? The electrostatic repulsion is going to be decreased. Therefore, the colloid, one colloidal particle and the other colloidal particle, then they can form coagulate. Ultimately, that will lead to the instability of the respective colloid. And here we have some list. You have to remember this list, students. The positively charged colloid and negatively charged colloid, you cannot do the experiment and decide what charge we have. We can actually do the experiment. If I have given a charged particle, I will apply the electric field. I will keep two plates, one positively charged plate, negatively charged plate, and observe the motion of colloidal particles. And from that motion of colloidal particles, I can say if they are moving towards positively charged, they should be negatively charged. If they are moving towards negatively charged, they should be positively charged. I'll say these colloidal particles possess this type of charge, and the reason for that charge I'll explain later. But that apparatus is not given to you in the exam. So if a particular sol is given, we have to know what type of charge is there in that particular sol. So positively charged salts and negatively charged salts, we have to remember examples: metal hydroxides and hydrated metallic oxides, they are positively charged. Basic dyestuffs like methylene blue sol, proteins in acidic medium, hemoglobin, they are all positively charged. Metallic sulfides and metals, they are negatively charged because of electron dispersion majorly. Acid dyes in basic medium like Congo red salts used in. Proteins in basic medium, Salts of starch, gum, gelatin, clay and charcoal, all these are negatively charged salts. Blood is a naturally occurring negatively charged colloid, but hemoglobin is a positively charged colloid. As I was saying, you have to remember the examples of all the positively charged salts and negatively charged salts. Is everything clear so far?
Yes, sir.
Yes,
Yes.
sir.
Until now, we have seen the reasons why the colloidal particles will possess charge. Now we will see the proof. Proof is nothing but I'll apply the electric plates. Electric field I'll apply. If the colloidal particles are moving toward the oppositely charged electrodes, then they possess charge. If they are not moving, they should not contain charge. Electrophorese provides an experimental proof to show that the colloidal particles are charged particles. So if electric potential is applied across two platinum electrodes dipped in a colloidal solution, the colloidal particles move towards one or the other electrode due to the charge on them. Due to charge on them, what happens? The colloidal particles will move towards one or other electrodes. The movement of salt particles under an applied electric field, that is said to be electrophoresis. The movement of salt particle under an applied electric potential, that is said to be electrophoresis. So you can see the animation. So we have the respective negatively charged particles. We have electrodes. All the negatively charged salt particles, they are moving towards positively charged electrode or not. This movement of colloidal particles under the application of electric field, that is nothing but electrophoresis. What is electroosmosis? Electrophoresis is the movement of colloidal particles. The movement of colloidal particles towards oppositely charged electrode, that is said to be electrophoresis. Electroosmosis is like if I am stopping the movement of colloidal particles, like somewhere here I have kept a semi-permeable membrane. If somewhere here I have kept a semi-permeable membrane, then what happens? All the colloidal particles will reach here only, up to here only. They want to move toward positively charged, but they are not moving. So then what happens? The extra positive, the extra negative charge is present here, right? So then what happens? The dispersion medium particles will move in the opposite direction. The movement of dispersion medium particles in the opposite direction, that is nothing but electroosmosis. That is, yes, Faizan Khan, generally the applied potential will be greater than the zeta potential only. The potential developed on the ions is very less. Whatever the external potential we are applying, that should be greater. Yes or no? The external potential, whatever you are applying externally, that should be greater. And in the zeta potential also, one layer is the diffuse layer. Okay. So that is not a disturbance because these charges, whatever developed on the electrodes, they are greater. So the motion opposites, like positive negative attraction will be there, and because of that, motion is going to happen. Electroosmosis means if the particles of colloidal system, if their motion has been stopped by some means, then the dispersion medium will be begin to move in the electric field. So the medium will move in opposite direction to that of dispersed phase. This will happen under the influence of electric potential. Electroosmosis, as I was saying, if the movement of particles is prevented by some suitable means, like a semi-permeable membrane, then it is observed that dispersion medium begins to move in an electric field. But in what direction? Exactly opposite to that of dispersed phase. The medium will move in opposite direction to that of dispersed phase under the influence of external electric field. Under the influence of external electric field. So all these are the different properties shown by colloidal particles. Is that clear, students? Is everything clear so far?
Yes.
Yes, sir.
Yes, right. Then we can have the concept of coagulation or precipitation of colloids. Coagulation means what? We have to form an aggregate. Why they are not forming an aggregate?
Because
Because of
ion-
because of charge, they are repelling each other. If by somehow or the other how, if I try to remove the charge, what happens? They will form the aggregate. Again, you can think of two perspectives. One is lyophilic and the other is lyophobic. Lyophilic sol is stabilized by what? Lyophilic sol.
hydration.
Hydration.
Hydration as well as charge. Charge is less, but there might be still some charge present. Lyophobic,
Charge.
charge. So if I want to coagulate lyophilic, what I have to do? I have to remove the hydration, I have to remove the charge. If I have to remove, if I have to coagulate lyophobic, then what I have to do? I have to simply remove charge. So coagulation of which sol is easy?
Lyophobic.
Lyophobic is easy. The process by which dispersed phase particles in a sol are precipitated, that is said to be coagulation. It is sometimes called as flocculation. What do you mean by flocculation? If the precipitate particles or the aggregates, if they are floating on the surface of water, then that is said to be flocculation. The process by which dispersed phase particles in a sol are precipitated, that is said to be coagulation. If coagulated particles float on the surface of dispersion medium, if the coagulated particles float on the surface of dispersion medium, then coagulation is said to be flocculation. For lyophobic sol, first one, for lyophobic sol, what is stopping them from forming a coagulate? Just a charge. The stability of lyophobic sol is due to adsorption of positive or negative ions by the dispersed particles, that is due to their charge. If somehow the charge is removed, there is nothing to keep the particles apart from each other. If the charge is removed, we have intramolecular force of attraction between one molecule of particle and the other molecule. So they will simply come and form an aggregate. In such cases, they aggregate or flocculate and they settle down under the action of gravity. Under the action of gravity, they will simply settle down. So coagulation of lyophobic sol, whatever the processes we are going to discuss, all these are trying to remove the charge. First one, by addition of electrolyte. If I try to add electrolyte, what happens?
New interactions are formed
Yes.
If I
because
try to add electrolyte, like excess electrolyte will reduce the charge because charged particles will have, the colloidal particles will have specific charge. The oppositely charged particles from the electrolyte will reduce the charge of this particular colloidal particle, thereby neutralizing it. So by addition of electrolyte, what happens? By addition of electrolyte, we can have the reduction of charge. By electrophoresis means movement in the presence of electric field. Once they reach the electrode, what happens? In the electrolysis, what happened? Deposition occurred. Yes or no? The oppositely charged ions, they will reach the respective electrodes, they will deposit there. So upon movement towards oppositely charged electrode, discharging occurs by mixing two oppositely charged particles. If I mix a positively charged particle with a negatively charged particle, what happens? The charge is lost again, neutralization occurs and precipitate formation happens. By boiling, with increase in temperature, what happens? The
rate of adsorption decreases.
Molecular motion increases, adsorption decreases, and the colloidal particles, whichever has charge, they will lose their charge. I have told you this repeated dialysis also. If you try to repeat the dialysis many times for longer time, what happens? Almost all the electrolyte is going to be,
Coagulation.
yes, almost all the charge is going to be, all the electrolyte is going to be removed, and thus charge is removed, and thus precipitation occurs. We'll see the same points. By addition of electrolyte, when an electrolyte is added in a solution, it furnishes both type of ions. Like AB is an electrolyte which dissociate to produce A plus and B minus. The oppositely charged ions get adsorbed on the surface of colloidal particle. This causes neutralization. Due to greater volume and greater mass, these particles settle down and coagulate. If you are just trying to add electrolyte, what happens? The oppositely charged ions, they will neutralize, thereby forming a coagulate. The ion responsible for neutralization of charge, that is said to be flocculating or coagulating ion. What do you mean by this? Like if Sol particle is positively charged Sol, positively charged Sol is there, and I have added an electrolyte AB. Which ion is responsible for flocculation or coagulating? For a positively charged Sol, if I add an electrolyte AB, which ion is responsible for coagulation?
B minus.
B minus. Okay.
B.
B minus will neutralize the charge, right? B minus is called coagulating ion because B minus is neutralizing the charge. Hardy's-Soule rules. The higher the valency of coagulating ion, like we have positively charged Sol, positively charged Sol is there, and we have B minus, C2 minus, D3 minus, E4 minus. Where you have more charge, the higher the valency of coagulating ion, the greater is its coagulating power. Can I say in E, we have 4 minus, that 4 minus will neutralize the positive charge greatly, thereby its coagulating power is great. For the precipitation of AS2S3, AS2S3 is what type of Sol? It is
Negative Sol.
Negative.
negatively Sol, negatively charged Sol. So we have Al plus 3, Ba plus 2 and Na plus. What is the order of their coagulation power?
Al plus 3, then
Al
Ba
plus 3
plus 2,
greater.
then Na plus.
Very good. Al plus 3 greater, then Ba plus 2, then Na plus. So more charge will be neutralizing the respective negatively charged Sol, thereby it has more coagulating power. Or the precipitation of FeOH taken as Sol. FeOH taken as is positively charged Sol. If it is positively charged, you have to compare the respective negative ions FeCN6 3 minus, sulfate and chloride. Out of these three, the complex ion has 3 minus, sulfate has 2 minus, chloride has minus only. So what is the order? FeCN6 3 minus greater, then sulfate, then chloride. This is the respective order. Yes or no?
Yes, sir.
Yes, sir.
And this point you have to understand carefully. The minimum concentration of an electrolyte in millimoles required to cause precipitation of 1 liter of Sol. I have taken 1 liter Sol. Understand it in this manner. 1 liter Sol you have taken. I am adding electrolyte. I am adding electrolyte AB. Its concentration you have to measure in millimoles. The minimum concentration of electrolyte in millimoles added to 1 liter Sol to cause the precipitation in 2 hours. In 2 hours, this 1 liter Sol has to be coagulated. For that to happen, how much is the concentration of AB in millimoles? That is nothing but your coagulating value. Like you have AS2S3 Sol. AS2S3 Sol, to coagulate it, I am adding 2 electrolytes A and B. Electrolyte A, whenever it is added, it is coagulating 1 liter Sol in 2 hours, but how much quantity you require? Only 1 millimole. But to coagulate 1 liter of AS2S3 Sol in 2 hours, we require some 10 millimoles of other electrolyte. One electrolyte is requiring only 1 millimole, other electrolyte requires 10 millimoles. So where the coagulating value is less? 1 millimole means coagulating value is less. Coagulating value less means where the power is high, coagulating power.
1 millimole.
1 millimole.
So I can say coagulating value is inversely proportional to coagulating power. Okay, read the question carefully. Sometimes they'll be asking coagulating power, sometimes they'll be asking the coagulating value. If you try to write the coagulating value of these ions, where it should be highest? Chloride will have the highest, then sulfate,
Cl
then
minus.
respect to FeCN6 whole 3 minus. The smaller the coagulating value, the higher will be the coagulating power of the ion. The smaller the coagulating value, the higher will be the coagulating power of the ion. Is that clear?
Yes, sir. Yes, sir.
Right, very good. By electrophoresis, electrophoresis is similar to electrolysis. You perform the electrophoresis, the ions will be moving towards oppositely charged electrodes. Upon reaching oppositely charged electrodes, they deposit there. During electrophoresis, the charged Sol particles migrate towards the oppositely charged electrode, get discharged and precipitated. By mixing two oppositely charged, here what happens? Mutual coagulation occurs. Because the charge, like positively charged Sol, I mixed it with negatively charged Sol. The positively charged Sol particles, they lose state charge. Negatively charged Sol particles, they lose state charge. Ultimately, mutually they coagulate. Oppositely charged sols, when mixed in almost equal proportions, neutralize their charges and get partially or completely precipitated. Partially or completely they get precipitated as charge neutralization occurs. This type of coagulation is also called as mutual coagulation because the positive charge of one Sol particle is neutralized by negative charge of other. That means the negatively charged Sol particles, it is also losing its charge. So mutually they are both getting coagulated. Example, FeOH taken as positive Sol and arsenic sulfide when mixed, they neutralize each other and they get precipitated. Like oppositely charged Sol you are adding and precipitation is happening. By boiling, because of boiling already the charged particles, the colloidal particles have charge. Because of boiling, the molecular motions increase. Because of increased molecular motions, what is going to happen? The charge will be decreased. Salts such as sulfur and silver halides dispersed in water gets coagulated when boiled. Why? Due to increased collisions between the salt particles and water molecules. The dispersed phase particles, they will also collide. Dispersion medium particle will also collide with the dispersed phase. Probability for which collision is high? Dispersed phase with dispersion medium is high. Why? Because number of dispersion medium particles are high. Like ultimately, we can say the collisions are going to happen with the salt particle with other salt particle with the dispersion medium particle. Ultimately, because of collision, charge is going to be disturbed. So whatever the charge which is going to present, if that charge is removed, the salt particles will get coagulate and ultimately they settle down. They'll get coagulate and ultimately they will settle down. Is that clear?
Yes, sir.
Yes, sir.
Yes. By repeated dialysis, if you do the repeated dialysis, what is going to happen? All the electrolytes have been removed. When dialysis is repeated again and again, then colloidal solution gets coagulated. So water you are flowing, water you are passing through this particular bag of colloidal solution. If you try to remove the electrolytes continuously, that particular colloidal system will have only the colloidal particles and they will not have the electrolytes. So ultimately charge will be removed, thereby they get coagulated. So these are the ways in which you can actually coagulate a respective lyophobic sol. Then for lyophilic sol, what you have to do? There are two factors which are responsible for the stability of lyophilic sol. What?
Charge
Hydration.
and nutrition.
Yes, very good. Charge and hydration. When these two factors are removed, a lyophilic sol can be coagulated. To coagulate a lyophilic sol, you have to remove these two factors. How the solvation can be removed?
Operation condensation.
Solvation can be removed by adding a suitable solvent. If you try to add a suitable solvent of other type, the already around the dispersed phase particle you have the solid molecules covered. If you add one more solvent, if that other solvent added develop new electrostatic force of attraction with the dispersion medium particles, then dispersion medium will develop new attraction with the added solvent and it will remove out the colloidal particle. Solvation can be removed by adding a suitable solvents which develops attraction with solvation can be removed by adding a suitable solvent which develops attraction with already which develops attraction with a dispersion medium phase, DM, dispersion medium. When solvents such as alcohol and acetone are added to hydrophilic salt, this is what I am saying. When solvents such as alcohol and acetone are added to hydrophilic salt, the dehydration of dispersed phase occurs. Why? Because the water is going to develop new electrostatic force of attraction with the alcohol and acetone. So it will leave out the colloidal particle and come out of that attraction and develop new interaction with the alcohol and acetone. So under this condition, a small quantity of electrolyte can bring about coagulation. You have added alcohol, and then if you try to add a small quantity of electrolyte, what happens? The charge is also removed. Because of addition of acetone or alcohol, the hydration removed. Because of addition of electrolyte, charge will be removed. Ultimately, they get coagulated. Clear or not?
Yes, sir.
But which are more stable when compared to lyophilic and lyophobic?
Lyophilic.
Lyophilic. So lyophilic salts have a tendency to actually protect lyophobic salts. This can actually happen like a lyophilic salt, they can form a layer around the lyophobic salt particle also. We'll discuss that. Stability of lyophilic salts, high solvation and less charge. Coagulation of lyophilic salts, high solvation you can remove by adding a suitable solvent. Less charge, that can be removed by adding an electrolyte. Protection or protective action. Understand this point carefully. Understand this point carefully. The protective colloid you are adding, that protective colloid is actually forming a layer. That means the protective colloid, whatever you are trying to add, that is lyophilic salt, the lyophilic salt will try to form a layer around the lyophobic salt, making the lyophobic salt more stable and won't allowing it to coagulate. So when a lyophilic salt is added to lyophobic salt, when lyophilic salt is added to lyophobic salt, the lyophilic particles form a layer around lyophobic particles and protect the lyophobic salt from electrolytes. The property of lyophilic salts to prevent the precipitation or coagulation of lyophobic salt, that is called as protection. The property of lyophilic salt, the property of lyophilic salt to prevent the precipitation or coagulation of lyophobic salt, that is said to be protection. Now with respect to this perspective, we have some definition also. Like gold number we have to define. We have to take respective 10 ml of gold salt. 10 ml of gold salt you have to take. To that you try to add 1 ml of 10% electrolyte. What you will add? 1 ml of 10% NaCl solution. Because of addition of 1 ml of 10% NaCl, this 10 ml of gold salt will coagulate. Now you will add the lyophilic salt. Understand the definition. Lyophilic salt added in milligrams. The quantity of lyophilic salt added in milligrams to protect or to prevent the 10 ml of gold salt, to protect the or to prevent the 10 ml of gold salt from coagulation upon addition of 1 ml of 10% NaCl. Is that clear or not? I'll repeat again, listen carefully. This is your respective 10 ml of gold salt. Imagine like this. This is your 10 ml of gold salt. To this, I am adding 1 ml of 10% NaCl. 1 ml of 10% NaCl is nothing but electrolyte added. Electrolyte, whenever I try to add to gold salt, it will coagulate. To that same salt, what I am adding? A lyophilic colloid. The quantity of lyophilic colloid added in milligrams to prevent the precipitation of 10 ml of gold salt on addition of 1 ml of 10% NaCl, that is said to be gold number. If gold number is higher, protection power is higher or lower?
Higher.
Lower.
Understand this? This is 10 ml gold salt. I have added 1 ml of 10% NaCl. Now, if I try to add just 1 milligram of a lyophilic salt and coagulation has stopped, it is protecting. And to stop the coagulation, I am adding other type of lyophilic salt, 100 milligram, where the power is high.
First case.
First case, yes or no? So gold number is the number of milligram. If the number of milligram added to prevent the coagulation of lyophobic salt, 10 ml of gold salt upon addition of 1 ml of 10% NaCl, if that is lower, obviously you have greater protecting power. Lyophilic colloids used for this purpose are said to be protective colloids. Gelatin, albumin, gum arabic, potato starch are some of the examples of protective colloids. So understand the definition carefully. See, 1 ml of 10% NaCl you are adding to 10 ml of gold solution, and also you are adding protective colloid. This protective colloid is actually preventing the respective coagulation. In the milligrams, how much you have added, that is nothing but a gold number. The lyophilic colloids differ in their protection powers. The protection power is measured in terms of gold number. The number of milligrams of lyophilic colloid that will just prevent the precipitation of 10 ml of standard gold salt on addition of 1 ml of 10% NaCl, that is nothing but a gold number. And gold number is inversely proportional to protective power. Protecting power greater means gold number should be smaller. Gold number should be smaller. Is everything clear so far? The protecting power and all,
Yes, sir.
Yes, sir.
Yes.
right? The smaller the gold number of a protective lyophilic colloid, greater is the protection power. That's what I'm saying. Protection power is inversely proportional to gold number. Same as the previous case, coagulation value and coagulation power. Coagulation value is the number of millimole gold number of some hydrophilic colloids like gelatin, egg albumin, gum arabic, potato starch. If you take, gold number is 0.005 to 0.01 milligrams of gelatin required to do the coagulation or to prevent the coagulation. So where the gold number is laced, smaller gold number indicates greater protection power. Smaller gold number, that will be indicating the greater protection power. This was the concept behind it. Is everything clear?
Yes, sir.
Yes.
Yes, right. Very good. So these are the, like we have seen the classifications of colloidal solution based on physical state of dispersed phase and dispersion medium. Then we have seen different classification based on lyophilic and lyophobic colloids. Then we have also seen the classification based on type of particle in dispersed phase, like multimolecular, macromolecular, associated. Purification of colloidal systems, dialysis, electrodialysis, ultrafiltration, preparations, Briggs-Stark method, peptidization, as well as chemical methods like double decomposition, oxidation, reduction, and hydrolysis. Then we have discussed different properties starting from visibility, filtrability, optical properties, Tyndall effect, kinetic properties, Brownian motion, electrophoresis, electroosmosis, charge, zeta potential, All these properties we have seen. After that, we have seen about the techniques of coagulation for lyophobic as well as lyophilic. In that process, we have studied about the protection power as well as Gould number. Similarly, in the coagulation techniques, we have seen about coagulating power as well. Right. After this, we are good to start with emulsions. Emulsions are what? They are liquid colloidal systems. Emulsions are not so stable. That is why we always require an emulsifying agent. So generally, one of the liquids is water. So there are two types of emulsions: water in oil type and oil in water type. There are two types of emulsions: water in oil type and oil in water type. So for stabilization of an emulsion, a third component called as emulsifying agent or emulsifier is usually added. And what are the two types? Water in emulsion, water in oil type and oil in water type. So water in oil type means what? Water in oil type means which is a dispersion medium?
Oil.
Oil.
Dispersion medium is oil. Oil in water type is dispersion medium is water.
Water.
Okay, emulsions, if you try to classify, oil dispersed in water, oil in water type, water dispersed in oil, water in oil type, oil dispersed in water, oil in water type. In this type, water acts as a dispersion medium. In this type, water will be acting as a dispersion medium. So examples on this category, if you try to think of milk, vanishing cream, all these are examples of this particular category. That is why in milk, since the water is a dispersion medium, if you try to add water, you cannot observe. We cannot observe like any change. Like without tasting it, you cannot observe. You cannot predict whether the milk is pure milk or the diluted one, because water is going to act as a dispersion medium. You can add water. Because of addition of water, there can't be any significant change which you can observe by just looking at it. Emulsifying agents for oil in water type are gums, proteins and soaps. These are the respective emulsifying agents. The emulsifying agents will actually try to stabilize the respective salt particle. Like emulsion, respective emulsion is going to be stabilized by emulsifying agent. If not, what happens? Coagulation can also occur in some cases. Water dispersed in oil type. Here oil will be acting as a respective dispersion medium. Oil will be acting as a dispersion medium, and examples of this type are like butter, cold cream, cod liver oil, all those coming under this category. Examples of this type are butter, cold cream, cod liver oil. In all these categories, you have oil will be acting as a respective dispersion medium. And what are the emulsifying agents for this type of category? Emulsifying agents in this category are, you will be having respective heavy metals, lamp black, all that will be coming under this category. Long chain alcohol, lamp black, heavy metals, also fatty acids. All these are the emulsifying agents. All these are the emulsifying agents for the respective water in oil type. Water in the oil type. Lamp black is actually a amorphous. It is actually a amorphous allotrope of carbon. Like carbon has many allotropic forms, crystalline allotropes and amorphous allotropes. What are the crystalline allotropes of carbon?
Graphite.
Diamond, graphite, fullerenes. In the amorphous allotropes, what do we have? Lamp black, charcoal, coke, all these are the examples. Yes or no?
Yes, sir.
Which is the purest form of purest allotrope of carbon?
Divani होगी sir.
Which is the purest allotrope of carbon?
Diamond.
Diamond is the kinetically most stable allotrope. Graphite is the thermodynamically most stable allotrope. The purest form of carbon allotrope is fullerenes. Why? Because in diamond and graphite there are presence of dangling bonds. Whereas in fullerenes, because of the structure, there is no possibility of dangling bonds, and it is also allotropic in nature. Okay. Lamb black is actually an amorphous allotrope of carbon. Emulsions can be diluted with any amount of dispersion medium. As I was saying, if you take milk and if you try to add water to any amount, you cannot identify it because water is acting as a dispersion medium. On the other hand, dispersed phase, when mixed, forms a separate layer. When you try to mix this dispersed phase, it will form a separate layer. But if you try to mix a dispersion medium, it will be not forming any separate layer, and you can dilute it to any concentration. The droplets in emulsions are often negatively charged, and they can be precipitated by electrolytes. In the emulsions also, we have colloidal particles whose charge is negative. So with the addition of electrolytes, what happens? Neutralization of charge occurs. Neutralization of charge occurs, and thus neutralization of charge occurs, and thus precipitation can be done. Right? They also show Brownian motion and Tyndall effect. The emulsions will also show the Brownian motion as well as Tyndall effect. And emulsions can also be broken down into constituent liquids by heating, freezing, and centrifuging. These are the respective properties. Because they are also colloidal particles, they also show the respective Brownian motion and also Tyndall effect. Emulsions can be broken down into constituent particles by heating, centrifuging, and respective freezing. Is that clear? Is everything clear with respect to emulsions or not?
Yes, sir.
Yes.
Yes, right. Then we have the next concept of colloids around us. We will discuss the colloids around us and applications of colloids in next class. After that, we will start the catalysis. Thank you, everyone. Bye.
Thank you.
Thank you.
Yes.